Alright, so we're gonna do some solving of linear systems with three variables. We're gonna do it all ourselves, and here's the first one. By first one, I mean exercise 3. Okay, so go ahead and write that down. Let's do this with me, please. So our three equations: x plus y minus z equals 2, and then 3x plus 3y minus 3z equals 8, and our third and final equation, 2x minus y plus 4z is equal to 7. So we have to get rid of one of the variables first, and it looks like it's going to be simplest to get rid of our y's, right? So the top equation, the bottom equation. Remember, what we want to do is label these things with an A, a B, and a C. So in order to get rid of the y pretty easily, I'm just going to go A plus C, right? Top equation plus the bottom equation. Let's go ahead and write it down. So we got x plus y minus z equals 2. And then on the bottom equation, 2x minus y plus 4z equals 7. Okay, add up our columns. We have 3 x's, y's cancel, plus 3 z's is equal to 9. All right, I'm going to go ahead and shortcut this. Let's go ahead and take a third of that and make the next equation x plus z is equal to 3. Right? Yes. So put a box around this, and let's call this one equation D. So since I got rid of y, I need to get rid of y again. And let's use B and C to get rid of that y. I'm going to change colors to make this totally colorful. Okay, so B and C. So I need to multiply C by 3. So how about B plus 3C? Just copy down B just like you see it. We got 3 x's plus 3 y's minus 3 z's is equal to 8. And the bottom equation times by 3, we have 6 x's minus 3 y's, and then plus, what do we multiply? 3 times 4, 12 z's is equal to 21. Okay, so far? Alright, now let's go ahead and add these two equations together. We get 9x, those cancel, plus 9z is equal to 29. Alright, okay. I can kind of see that there might be a bit of a problem here, but that's okay. If you don't see it, don't worry about it. Let's just change colors to maybe green here, and now I'll get rid of either the x or the z. Oh yeah, I didn't label that one. I need a letter for it. Right, let's call this one, let's block this one off. This one's equation E. There we go. Now I'll change to green. There we go. So to get rid of, let's just get rid of the z's. Man, stinking z's. Overly complicating things. So how about I do a negative 9d plus E. That should do the trick. So negative 9 times d should be a negative 9x minus 9z is equal to negative 27, right? Because 3 times the 9. And now let's pair it up with equation E. 9x, do you see what's happening here? Maybe you see it now. It's equal to 29. Let's add those two equations. So what happens is that the x's cancel and the z's cancel, and I get 0 is equal to 2. If at any point I get a contradiction like this is a contradiction, because there aren't too many places on the planet where 0 is equal to 2, I'm going to conclude that there is no solution. So let's look at, on Microsoft Mathematics, what this thing is supposed to look like, okay? So should be right here. So it looks like we have two parallel planes and one plane cutting across them, so they don't all three intersect at the same place. Okay, on exercise 4, we're going to solve this system of equations. go ahead and write that thing down. X plus y plus z equals 6. X minus y plus z also equals 6. And then finally 4x plus y plus 4z equals 24. Step 1, label your equations. So let's go with A and a B and a C. Okay, what do we want to get rid of first? Well, let's take a look. Well, it looks like it's going to be really easy to get rid of the y's. So let's use A plus B to get rid of the y. So A plus B. So when I do A plus B, let's write them down. X plus y plus z equals 6. X minus y plus z equals 6. And let's add them up. 2x's, no y's, plus 2z's is equal to 12. Hey, those are all even. Let's take half of it and go x plus z is equal to 6 and box this equation off as D. Okay, so we got rid of y once. Let's get rid of y again. Let's go back to the drawing board here. And if I use, I could use B and C together, the y's would cancel out again. I don't have to do anything special. So let's do B plus C this time. So x minus y plus z is equal to 6 again. And then 4x plus y plus 4z is equal to 24. Add them up. I got 5 x's canceled and 5 z's. Whoops. 5 is equal to 30. Let's go ahead and take a fifth of that. Right. A fifth of that. There we go. X plus z is equal to 6. Man, that equation looks mighty familiar. Equation E. Wow, equation E and equation D are exactly the same thing. What's going to happen if I, say, subtract those equations from each other? I should end up with 0 equals 0. Let's just take a look at that, all right? So I'll go ahead and switch colors. Let's do purple this time. Okay, so let's go with a negative E plus D. So a negative x minus z is equal to negative 6, and we're going to add that to x plus z equals 6. This should be so much fun. Oh, those cancel, those cancel, those cancel. I get 0 equals 0. Indeed, that is a true statement. It's identity. Well, there we go. I didn't it. Pitiful. No, eraser. Okay, I'm going to try this again. Identity. There we go. There we go. And which means that we have infinitely many solutions. This pen can't keep up with me. I'm just writing too fast. Solutions. And, well, here's the question. I wonder if there is a more convenient way to write those solutions. Like, what if I wanted one of them? How could I find one of them? Before we talk about that, before we actually do that, because we are gonna, let's just look at what this thing looks like. Oh, look at that. They all intersect at one line. Okay, so if I could get the equation of that line, say, I would have every single solution, right? But what we're going to do is we're going to write it as a generic ordered triple, so that all we have to do is plug in a number and we can get any single point that is on that line, any single solution to this system of equations. Okay? So when you discover that you have a consistent dependent system of equations, so you've got infinitely many solutions, how are you supposed to write your answer? So we know that all of these planes are supposed to intersect in a line. You could write the equation in a line, but specifically we're going to write them as an ordered triple. So this is what we're going to do. To write your answer as a sort of a set of ordered pairs. What? A sort of ordered. Fix this. Triples. Okay. Set one of your variables in your equation equal to a. So you might be going, well, why don't I just use x, y, or z? We're just going to get it away from those variables x, y, and z, and we're just going to make something general, like a, that I can stick any number into it. It doesn't have to be a. It could be your favorite variable as long as it's not x, y, or z. Okay, so we're just getting away from those variables. So I could choose any one of them, right? And so I'm just going to go ahead and choose x. I'm going to let x equals a. And now I'm going to take that bottom equation, I'm going to put the a in there for x, and now I'm going to solve it for z, so that I can get an expression for z in terms of a. I don't solve it for a, I solve it for z. So subtract the a over, z is equal to 6 minus a. So I have an expression for x, it's a. I got an expression for z in terms of a, it's 6 minus a. Now let's plug all two of those, x and z, into the original equation, the top equation there, and get something for y, okay? So when I do that, the a goes in for x, and the 6 minus y goes in for z. Well, these a's are going to cancel out, and the 6 is going to subtract to the other side, and you're going to get y equals 0. Which means that no matter what, whenever you solve this system of equations, y coordinate is always 0. But then the x and the z coordinate can change a little bit. So this is what we're going to do. This is how we're going to write it here. We're going to write it as a generic order triple like this. A, because that was our x coordinate, comma 0, comma 6 minus a, right? We probably would have run into some problems if we chose y to be a, because I couldn't have gotten anything to relate to x and z. So what you always want to do is take the equation that you get once you simplify it down. Like, you get the equation twice. For us, it was x plus z equals 6. Okay? If you get that equation twice, you know you're in business. That's the one that you're going to choose one of those two variables to make a. Okay, we chose x. We could have chose z. Anyway, now all I have to do is make a equal to whatever I want, and I can get an ordered triple on that line. So, for example, if a is equal to 0, I get the ordered triple 0, 0, 6. Right? Just plugging 0 in for a. If I let a equal 1, I would have 1, 0, 5. Or maybe I let a equal -1. I'd have -1, 0, 7. And you can let a equal whatever you want. You can have an infinite number of these points. Okay? So that's what we want to be able to do if we run into a situation where we have infinitely many solutions. Okay? So here's your chance to practice what you've just learned or slept through. I don't know. You be the judge. Okay, so you have 3 linear systems of equations, and you might be thinking, I'm probably going to get one with one solution, one with no solution, and one with infinitely many. But you'd be wrong. You'd be wrong if that's what you thought. Anyway, so I want you to go ahead and try to solve those yourself. So pause the video, write down your system, solve it out. It might take you 20 or 30 minutes, and then come back and you'll probably have to restart your computer after that because it will go to sleep. And check to see if you got your answers right. All right. Okay, so you're back. So were these your answers? So the first one turns out to be, it intersects at 1 point, 1, 3, -2. The middle one, no solution. And the last one, infinite many solutions. Yes, I lied to you. And writing it as a generic order triple in terms of a, 3 minus a, 0. Now, if you need more details than this, what I have in this video, just look right down below. I've scanned in a part where, like some pages where I worked them all out by hand, so you can see step by step what I did. Okay, so if you need that for some help, open up that PDF file and take a look, okay?